Today we are going to do section 1.10 on page 48. So first let's take a quick scanning of books. Here's the answer sheet again. And then next let's look at page 48 and 49. Okay, here is the entire page. Okay, that looks all right, I guess. And then here's zooming in on the top and zooming in on the bottom. Okay. Next, on page 50 and 51, we have, let's see, okay, that's the top of the whole page. Then zooming in on the top of the page and zooming in on the bottom of the page. Okay, that's it. Now before we start the section, I want to quickly remind you of certain matrix properties in case it's been a while since you looked at it, so they don't look as familiar. Now here are the matrix properties. The first, if you take factor out something from a row or column of a matrix, okay, that's the same as just factor out that thing. Okay, that is, if K goes across the first any of the rows or columns, then you can just plug it right out. Another thing is the determinant. Of course, the determinant of a matrix is the same in a transpose situation. That is, you can write A1, A2, A3 across, or A1, A2, A3 down, etc. And the determinant of the two matrices are the same. Okay, and then finally, remember how to multiply these things. Okay, to multiply matrices, you have to take the row on top and to do the dot product, as it shows here, of the row that's on the left. Okay, and one at a time, and that gives you the first sum. If you don't remember that at all, please look that up. Okay, to remember exactly how to do this. So anyway, and finally, we need to remember this theorem, that is the determinant of two matrices when you multiply them together is the same as the determinant of multiplying the matrices first with that trick, okay, and then calculating the determinant. So that's that. And with that, we can start our section 1.10 Jacobians. Now the subsection 10.1 about implicit functions, we have already talked about all of this. This is just a summary of what we learned in the earlier section. So please read this yourself, okay? And to refresh your memory in this matter. But I'm not going to go over it. So we can move on to subsection 10.2, the inverse of a transformation. A transformation is a set of functions that take something from, say, the xy space and toss it to the uv space. Those things are called transformations. Now the transformation will contain the Jacobian, and if the Jacobian isn't zero, then we have the inverse transformation where you toss things back out. Okay, that is, you take something from xy space and throw it back to from the uv space, and then throw it back into the xy space. Now so we'll call that Jacobian the small j. So the big J and small j turns out to have some kind of a relationship. Okay, now so we will see the book did some calculations here, right? And to investigate the relationship between the small Jacobian and the big Jacobian. So I did the same thing. I just wrote it all out. So please do this yourself. Okay, just the calculations. And what it is here's big J, right? And there's small j, and small j is defined, as you can see, is end up being partial x, partial u, etc. And how are we going to do that? Well, we're going to do it the old-fashioned way. We need to crank them each out individually by doing this old trick, okay, that we did in the implicit function section, right? And then apply the Cramer's rule out of this two equations, two unknowns, so we were able to crank that out and eventually end up with the answer on the other side, being that there's a zero in here, so which make the answer simpler. And remember that the big J is defined, it happens to be what's on the denominator here, okay? If you double check the big J. which is fine. So eventually we calculated partial x, partial u, and partial y, partial u, and we're going to do the same thing with partial v's, okay? And we calculate the same set of equations, and we crank everything out. And so please do this yourself. This takes a little bit of time, but it's not a big deal. It all comes out pretty quickly. And so when you did all that, then you realize that the small j, once you plug in the partial, small j anyway, so the small j as defined up here is the bunch of partials, right? So once we calculate them out, we plug them all in, and which means that we will have it will have a common factor of well, anyway, it will be equal to this, because each partial x partial v, for example, is divided by j, so we can pull it out. So there's two rows of being divided by j's. Remember I said that if one row has a common factor, you can pull it out. And now both rows have common factors of 1 over j, so we end up with 1 over j squared in this matrix. And then by the time we, but this thing itself also happens to be j as well, okay, when you do the math. So when you do, and once we end up getting the division done, this little j is just 1 over big J, which means big J times little j equals to 1, and that's what we're trying to strive for here. And this is just, please do this yourself. This is just a matter of, cranking out the algebra, basically. So then we end up with big J times little j equals to 1, which is helpful because if you write it out, that just means partial uv, okay, against partial xy, and times partial xy, partial uv, and you see, you sort of visually can cancel it out, pretend to cancel things out, and it equals to 1. So it's somewhat easy to remember as a result. This lucky coincidence. And then, so now, next, let's look at 3 variables. What happens with 3 variables? We're going to do a similar thing. However, with 3 variables, things get hairy very quickly. And when I say that, I mean there's a lot more work. Okay, you have to write out all these partials, and there's 3 equations, simultaneous equations, and so on. So you have a lot of writing going on. But we're going to do that anyway. Okay, so then to start with, of course, we have the same principle. We have the functions, right? And we have a big J, which is defined like this. Now we have U, besides UV, we also have W, so we add that in. So the small j then, of course, is just the big J flipped around, upside down, and but everything stays the same. So then the big J, we know that the big J is defined as this, okay? And then we need to calculate what small j is, and that's when things get confusing. So I have it written down here. So we have, as the problem states, see, the big J is that, and the small j is all the partial that we need to calculate all 9 of them, okay? And so that's what I'm going to do. So first I have taking the partials against u, then we have the same way we always do, okay? Just like the previous case, the 2D case. Now we have 3D, but things don't really change. And that much. Well, we have more work. So we have three equations, 3 unknowns, and by the time we calculate it, then, well, first partial x, partial u, you realize that it equals to that thing, okay, over j, because we substitute 1 here, okay. So then the little, the determinant of the little one down here, which I wrote over there, is going to be end up what partial x, partial u is. Now the book decided to call that little thing down, that's the small determinant down here, it has a name to it. It's called the cofactor. And the book named the cofactor of this thing F1, okay? The reason it's called F1 is because it comes from the original F1 here, okay, this thing, being replaced by 1. So it's called big F1 as a result. So, once you see that, you realize what's going to happen. That's just partial x, partial u. We have 9 things total to calculate, and we're going to do them all. Okay, so please take your time to do it. You say, well, I don't really want to do that. Well, I did it. right? I mean, so can you, trust me. It's not, I'm really lazy, so if I can do it, so can you. So please do that, okay? So here's next. I wrote it all out, well, most of it. Partial y, partial u, right? And then partial z, partial u. So now you got 3 down and then 6 more to go. And similarly, because the way this is done, the partial x, partial v is the same thing except you move 1 down 1 slot. So you can just look at that thing and then imagine the 1 being moved down to the middle, and instead of writing this out, you could just use your imagination, move 1 down to the middle in your mind, and then do the partial x, partial v that way. So that way you can save a bit of work, okay? Then you do partial y, partial v, partial c, partial v, and so on. And we'll name those little matrices G1, G2, and G3. And similarly, we do partial x, partial w, same way, okay? Now the 1 got moved to the bottom, and then you stare at this thing and then write all this stuff out. It is faster, in my experience, to just write it out yourself than try to understand what I'm writing. Okay, it just so please do write all this stuff yourself, and then so eventually we that's how we got to this interesting matrix that your book has that they call the determinant of cofactors. Okay, and so here's our determinant of cofactors, and what are they? The determinant of cofactors just end up being is is related to the small j. That is, small j, as we have mentioned earlier, is the partial derivatives, right? And once you plug all this, and being that each item, the partial derivatives, is each item, as you can see, has to do with a small plug in. So if you look at it carefully, you notice that the small j is the k divided by j to the power 3, because each item in there is just the partials, except that they're all divided by j. So you're basically divided, each row got divided by j, so there are 3 rows of j's being divided, so you have dividing by 3, but otherwise the k is what the determinant end up being. So that's what small j is. Small j is then k over j over small j equals the k over big J to the 3rd power. Okay, so far so good, right? Now we are going to multiply these things together and see what happens. Now once you multiply it, you will realize that it happens to be equal to everything becomes 0 except the stuff across down is all j. And so the answer will be J3. Now I did the actual calculation, I believe, and well, I sort of did it. Okay, so then well, we're gonna do the actual calculation. Well, the way I did it is I did actually the matrix multiplication. That is, remember I mentioned a while ago, to calculate the product of 2 determinants, you can multiply the matrix together, the way matrices multiply, and then calculate the determinant. Okay, that's one of the rules. So knowing that, then we are going to take the first row multiplied by the first column, like you do in matrices, right? Which we get this, and you do that, you will quickly notice that that happens to be j. Okay, and similarly, the second row in the first matrix multiplied by the second column is also j. And it just, if you look at it carefully, the definition, you'll see why. So please do that yourself. Okay, so that's why that we have this situation where where the answer is j down the diagonal. And then the next thing we need to show is that everything else has to be 0. Okay, so I did that. Now let's consider f times g. Okay, so we know that the small f times big F, it end up being j. But what if it doesn't multiply by f? So say small f, we take the first row times the second column, right? And from the first matrix to the second matrix. So if you do that, then I wrote it out, and I quickly realized that you have 3 groups of identical stuff being subtracted. So for example, like the stuff I circled in red, well, that's not much of a circle, but Anyway, yeah. Anyways, you notice that they subtract themselves out. So you have three pairs of things all subtracting themselves out, and it end up being 0. And that's why the other things are 0. Another example is, so then I did the third one, okay, which is the first row times the third column. So F times the F's, the little f's times the big H's, same idea. You notice quickly that everything canceled out. Okay, there are three pairs of identical objects being subtracted, and so it's all gone. So then, in that case, then we have this situation, as your book asserted, that j times k end up being j cubed. Okay, if that is the case, then we'll do some math. If j times k equals to j cubed, what does that mean? That means, let's see, okay. Now, remember, what is small j? Small j, then, let's see. Okay, remember that small j, okay, we calculated earlier. Small j equals to k over j cubed. Now, so then we take the fact that j times k also is equal to j cubed, and then so then you plug things in, then you very soon realize the k canceled out, and small j times big J equals to 1. Okay, so that is how we got to the end. You notice that this is quite a bit of work, but please go over this yourself, just like I did. Okay, I mean, if I can do it, you can do it, right? So with that, so let's move on to the next page, which is okay, page 50. Next, let's look at page 50. We have a change of variable situation. That is, u is then x and y and all that, right? U is f of x or y, and so is v, g of x and y. Then x itself is something else of r and s, psi and phi. And if that is the case, then we have we will be interested in uv all the way down to r and s. And to calculate that, we will crank it up like we always do. Okay, we just do all the calculations by hand. So like this. First, what is uv rs? And partial uv partial rs. It will mean by definition this thing. And where each of these things ur means partial u partial r, etc. So then we have this thing, which is, so I calculate each item out, okay? As you can see, based on the function definition, that's what it's going to be, similar for Vs and so on. So once we know that, then we plug it into this equation, and we quickly notice that the partial uv partial rs, that is that thing, is the same as these two things, these two matrices multiplying by each other. Okay, so you have the first row times first column, you end up with that, right? And similarly, first row and the second column and so on. And anyway, yeah, this all works out if you double check it. And so this is the same as, of course, this thing is UVXY, and that thing is XYRS. And that's how we got it to all come out. So please just do this yourself. It's just a matter of verifying. I noticed that I made a mistake here, okay? I mean, it should be VR, right? And then VR, of course, is 1 instead of 2 or something like that. But you can figure that out easily enough. It's an obvious mistake. So having said that, we are done with this section. It's time to do homework. Now for homework, please do these problems I have, which is problems 1, 2, 3, 4, I guess. And for problem 2, you just use equation 2. And that's good enough. It says also do something else. I was too lazy to bother. Okay? So anyway, 1, 2, 3, 4, 6, and then 8, 9, 10, 11, 12, and 13. So when you're done with the homework, come back and I want to talk about them. Okay, now you're done with the homework. Let's look at it. Problems 1 is, I think, fairly straightforward of applying the equation 2 on the same page of the homework, where we have some formula. Okay, we just plug we plug everything in, and it all works out nicely. That's about it. And so problem 2, I think the same thing, even shorter. We just follow the formula in equation 2, and out pops the answer. Okay, and next, problem 3, which is on this page. I think a similar situation where we have 3 variables, 3 functions right now, but nothing's different, okay? We have that equals to this, which then equals to that, and it happens to be the answer. That was about it. Problem 4, the same thing. Okay, we just have a situation where we write stuff out, and it turns out to everything subtracted nicely, and it all collapses into 0. Nice. Okay, and then problem 6, where we have to solve some simultaneous equations. We have say, I did that, but I was not happy doing it. Okay, we have UVW equals to some system of x, y, z. And then, of course, we can do it by Cramer's rule, which was a real pain. So I looked on the computer until I found some free program that has. I will put this link down here. This is Wolfram Alpha's. They call that, can you see that? System Equations Calculator. Oops. Okay, the Systems Equations Calculator, which allow me to type in these 3 equations, and out pops the result, even in terms of variables. Isn't that awesome? Yeah, so that I didn't have to go through the work I did. Okay, so I was much happier to see that, even though I did already go through the work, but I really did not want to do the work. So getting it by the calculator, I also was able to confirm that I was correct. So life was much better. So anyway, so I calculate the j, right? And then from this one, and calculate the small j from that set, and then notice, hey, check this, they equal to 1. How awesome. So that's problem 6. Now next, let's look at problem 8. At first, when I tried to do problem 8, I was like, oh no, this is so much writing. I wanted to skip it. So I skipped it. But then later, after I did certain other problems, I thought back and I thought maybe there's a way to do it without wearing myself out. So I decided to attack it again and was able to get to the end. Okay, so here's the problem, right? And we're trying to calculate a whole pack of partial derivatives. So that's what we're gonna do. And so first we are doing the partial fg, and then against partial yc and partial yc partial uv. And that isn't as bad. See, I wrote that out. Okay, that comes out fairly straightforward. And then that equals to that stuff on the other side. So far, so good. Now, so I continue doing that for the other versions against zx and then against zy. And then I wrote all that out. I didn't multiply them out, but I noticed that there's a total of 12 terms. That is, each one is a 2 by 2, so 4 terms, 3 of them, 12 terms, right? So far, so good. So there's the 3. And next, I need to do partial fx and partial uv, right? And then, so following the rules, I calculate this thing. And what is that? This thing is that those 2 things multiplied together and minus those 2 things multiplied together, which is, that's a 3 by 3, that's so 9 terms, and then 9 more, so that has 18 terms. And we have to show that this equals to those 3 added together. But we have 18 terms here and 12 terms there. So how is that possible? So I looked at it very carefully, and I noticed that out of this thing on the bottom here, okay, 6 of them are canceled out. That is the identical, which I have written down here. As you can see, you notice there are 6 items that will subtract out, okay, because they're identical and there's a subtraction, which means there are 12 terms left in this expression. So we have to make sure that the 12 terms left here are identical to the 12 terms here once you multiplied everything out. So what I did is I checked each term in here that wasn't canceled out, okay, against the terms here. And then I was able to confirm, as I say right here, even though I didn't write it out, I said right here, all terms accounted for. That is, you will check this, okay, this part, against this, except for the ones that got canceled out, everything will be equal, okay? They're term by term identical. Each one you can find the other one in above, and that's why the problem 8 works, is that the two, what is problem 8? Yeah, you're supposed to show this equation, okay? And this equation works because I checked all 12 terms. Each term has four variables with subscripts multiplied together, okay? Maybe in different order. So please do that. And check all 12 terms, and then, well, actually, what I mean is, please write that out, okay? All 12 terms, top and bottom, and then you can show that they really are the same. I am not going to bother with that, but you should really do it. Okay, so that is problem 8. Now, problem 8 was a bit of a pain, but problem 9, on the other hand, is quick and smooth. Okay, let's look at problem 9, where we have, we're just changing variables, right? So we need the partial GH, partial UV. So F will be changed to G, and G will be changed to H. And plug it right in, and then everything will come out immediately. That is, I just replaced the names of things, okay? So, and that's that. So next, let's look at problem 10, where we have a similar calculating situation, but the situation is fairly straightforward, luckily. We have X and Y, and then equal to F and G, and then have some kind of H. Well, we calculate the J, big J, and then calculate various things and show that they are, they are what the book wants it to be, okay? It's just a quick and short calculation. So that's that. And then we will go to problem 11. Problem 11 is, again, a similar situation, but this time it's not so quick or short. I had to write out 2 pages of stuff, so I have it scanned in here because I think it's easier for you to see. Now, what happened is we have F and G. The book doesn't say it, but does it say it? Doesn't matter. The point is F and G equal to 0, okay? Where we will imagine U will be U and V functions of X and Y. So then we calculate first, take the partial derivative with respect to X of both equations. We get something like that. And then, so then we are able to calculate Ux and Vx, right? And then come up with something. And we will call this thing, the determinant of this, as the triangle, because that's how we call it sometimes, all right? So then we calculate Ux and Vx like we always do. Similarly, Uy, Vy, same thing. Remember to call that the denominator the determinant triangle. And then eventually, then of course, we have, next we calculate this thing, which is Ux, Vy, Vx, Uy, which we just calculated one of these things, okay? We need to plug it all in. So we get this big pile of stuff. And remember the triangle, then we have 2 triangles in the denominator, okay? Triangle squared. And then we will check and check for canceled terms. And we check that there are, I believe, 4 terms that are canceled or something. Yes. And yeah, there are 4 terms that got canceled, which will make life somewhat easier for us. But in any case, we keep going. Then we calculate FG against partial FG against partial UV. And that is just a triangle, right? And then partial FG, partial XY is that stuff. And then eventually, we calculate that then partial UV, partial XY is equal to that. And that would be, after some things that come out, that does equal to whatever is supposed to be equal to, okay? And so this is just a matter of doing a whole bunch of algebra and making things come out. Oh, I should mention that there's some factoring going on right here. Things, once some of the terms got canceled, the rest can be factored nicely to look like there's a triangle on top. okay? And then cancel out with a triangle on the bottom so that the formula we are trying to prove falls right into place. And then after that, even then we are not done yet. We are supposed to do continuing, let's see, where is it? All right, we continue to do problem 11. There it is. Okay, we have to verify something. So let's verify it. To verify that thing, okay, we have the U and V, so we will define big F and big G like that, and then verify it according to what we just proved, okay? Write down all these Jacobians, and then check and see, you see, being that this Jacobian happens to be 1, then of course, then this thing does come out very readily. And it's not much of a check, but it does work. All right. Next, let's look at problem 12. Problem 12 is asking you, well, what happens when you flip it around from the previous problem? Well, then we'll just exchange variables, okay? And we'll call x will exchange with u, and y will exchange with v. We'll come up with exactly the same thing. And therefore, this case works, because, well, we just flip this thing around. And that's all I want to say about that. So now let's move on to problem 13, where we have this function, and we have to calculate partial uv against partial xy. Okay, so let's do that. Okay, and following the formula given in problem 11, because that does make it easier. And so we plug everything in, right? First part, we just have to do partial fgxy, which is fairly simple to do, and fguv, again, fairly simple to do. And then once you got that, you multiply them together or something, and realize they all end up becoming just x. How nice. So now that we're done with that, we have to continue verifying by actually plugging u and v out, and then do it the direct way. So we did that. So see, we have x and y, this is the x and y equation. I pulled it out of there somehow, and then of course we end up with two solutions, but I decided we'll just stick with a positive one and call it done, okay? Because we're just checking something and I don't want to bother. So then we'll stick with the positive solution. So u equals the positive x cosine y, and then you plug in the v, and so on. And then if we take the partial uv, partial xy, and everything comes out and falls apart, and cosine and sine becomes 1. How beautiful, right? And we end up with x, just like the other attempt. So we know that we must be getting everything correct. And with that, I believe this is the end of this section.